You know what it looks like? It's literally yeah. Some sort of it's kind of like the last
to the doc cam. There is some problem with the doc cam, we will have to use the slides. So we will have to use the slides, and I will also use the board in that case. So we were discussing Lamport-Bakery algorithm. So let's continue our discussion of Lamport-Bakery algorithm. This is the in-process critical section linear distribution problem. So let's talk about it. So last time we talked about one criteria. Let's revisit that criteria. So we said that there is something called num I, and this num I has n elements. So n because there are n processes. N is the number of processes. So there are n processes. The people in the back can see what I am writing. You cannot see? You can maybe come in front. Because today this doc cam is broken. No, it's broken. Still broken. Yeah, it's broken. It's not focusing. No. So we declared okay, there is an array, and the array has a number for each process. And we said that we use a new type of operator. This operator is num I less than num j. So typically the less than operator is only defined for numbers, but here we are defining the less than operator for some tuples. So how does that work? So this will return true or false. We said this returns either true value or false value. So this is true for two circumstances. So it is true first if num I is less than num j. Whenever that happens, it's always true. Right? And the second case, it is true when, let's say, num I is equal to num j. If num I is equal to num j, then this is true if I is less than j. That's what we said. And it is false for all other cases. That was what we said. So we understand this operator because we saw some examples. Right? So now let's talk about this Lamport-Bakery, since we understand this operation. So now instead of looking into the entire algorithm, let me strip down the algorithm for it. Let's write a different version of this algorithm. At the end. So let's write a different version. Before we go any further, so what is this first line doing? Yes. So conceptually, what is it doing? So nouns, as we saw last class, can be regarded as tokens, right? So you go to a doctor's office, you pull up a token, and whoever comes after you gets a number that is higher than you. Right? So it is like a token. So whenever a process arrives, it first looks at all the numbers that have been already taken, finds the maximum of who has the maximum number, and just takes the next number. Okay. So that is this process doing. Okay. So the process comes in and wants to wait for the wait to run the critical section. So the process of waiting is to take a token. So in order to take a token, it has to understand which one is the maximum token number that has been already taken. So that's what it finds out using this max operation. So finds out the maximum number and then just takes the next one. So adds 1 to it. Right? So that is the first line. Then what is it doing? The next for loop. So for the next for loop, let's again strip down the for loop. So in the for loop, it is looking for all the processes, 0 to n minus 1. So it is iterating through all the processes. Now doing what? So let's see this. For each process, what it does is this. So it does this thing, this while loop for every process. What is this while loop? It first checks, okay, has the process gotten a token? Right? If the process didn't get a token, then the number will be 0. Right? Because the minimum token will be 1. Because you find out the maximum and add 1 to it. Right? So if no processes came, everybody has 0, so your token will be at least 1. If you want to execute the critical section, then the processes, the minimum token number a process can have is 1. Right? So if it is not 1, then that means you don't want to execute critical section. So if you don't want to execute critical section, I won't consider that process. So process number I says that, okay, if you don't have a token, I am not worried about it. So that's why num j is not equal to 0. If num j is equal to 0, immediately break from the while loop. Don't even bother. But if num j is not equal to 0, then you have to bother about that particular j. right, the jth process. So if num j is not equal to 0, which means that you have a token, then what does I do? I checks this condition. Num j comma j is less than num I comma I. Which means what? That if the token is less, if j's token number is less, then this particular process will wait for j to finish. Why? How will it wait? If j's token number is less, this will return true. If this returns true, this returns true, and num j is not equal to 0, so that is also true. This is like a busy wait. Like you just get blocked. So you wait for the jth process. Now what if num j is equal to num I? What if you have the same token? If you have the same token, then I will see whether you arrived earlier or not. J is less than I or not. If you did arrive early, then I will still wait for you. If you didn't arrive early, I will break from the while loop and I will execute my critical section. So it looks for all the processes. It's not just one. You look for all the processes. So whichever has the lower token number, whichever arrived early, you wait for them. Now if you see that there is no other process that has lower token number than you, and there are no other processes which have the same token number but came earlier, then you can move. Right? So then what happens after that for loop? You execute the critical section, and once you are done with the critical section, then you set your token to 0. So that is the algorithm. Now note that we have eliminated choosing, that there is a choosing variable and I didn't use it, but we'll come to that later. But can we argue that this algorithm has can lead to mutual exclusion? Because that is the most important thing. If it doesn't lead to mutual exclusion, then it's not a solution. So if we just analyze this algorithm at a very high level, don't go to much detail, can we argue that this will give us mutual exclusion? So how will we argue? We'll say that yes.
Well, you're obviously choosing every process. You're always choosing the process with the lowest token. So you can check the first and the second step because T1 will enter first and T2 then enters depending on the token number. And for the last one, if T1 and T2 both attempt to enter at the same time, then the condition of checking which one has the lowest token will prevent them from executing.
Yeah. So what she is saying is that okay, you can in num can only have one value, right? Because the maximum of all nums will be only one value. So if maximum of all nums is one value, then if two processes come together at the same time, if two processes come at different times, then obviously they have different tokens. If they have different tokens, then one will wait for the other. And whichever is more will wait for whichever is less. So if two processes come at different times, no problem. They have the different tokens. But if two processes come at the same time, they might have the same tokens. They calculate max and the max values are the same. They add 1 to it and store. So they have the same tokens. But they will have different process IDs. Because these are two different processes. And depending upon which one came earlier in the ready queue or in the init queue, depending on which one came earlier in the init queue, they will have different process IDs. One will be less, one will be more. And whichever has a greater process ID will just wait. Or whichever has a lower process ID. Yes.
Aren't the process IDs recycled so you could get a later one having
We'll
some?
come to that a little bit later. So right now let's assume that they are not resulting. So the point that he raised alludes to the fact that this is not practical. This algorithm is not practical. You cannot implement this algorithm. And you can implement in a very restricted number of processes, but you cannot implement in general. So that is what he is saying, but we'll come to that a little bit later. But let's say that there are n fixed processes and you have n unique IDs. If you have n unique IDs, then this will give you mutual exclusion. But there is a small little catch, and that breaks down the entire mutual exclusion argument. So this solution does not have mutual exclusion. Can you tell me why or how? Can you give me an example where two processes can enter the critical section at the same time in this algorithm? Take me 5 minutes and try to see. So consider two processes coming in at the same time. Consider that and then figure it out. So take 5 minutes to argue. So forget about choosing right now. Don't matter what you are choosing. Okay, without discussing with each other, can you think about the problem? Don't discuss with each other. Yes.
Do you want us to say what you're looking for?
Yes.
I think if num j does not equal 0, it's checking the other process wants to execute. So if we have two processes and one of them says that they don't want to execute and then they change their mind and who want to execute after we pass a while condition, then we have two processes.
So what is the example here? Give me an example. Just let's walk through a process configuration. So what are you saying? Two processes that come in and what they do?
So the processes may have the same token number.
So they have same token number, which means they came at the same time and they have the same token number. So then what?
And then the second condition after the AND logic of the while loop is true for both processes. But
Why? If they have same token number, they will have different process IDs. So one will be true, one will be false.
But I guess we're not worrying about the process ID being.
No, I and j. So that's why you have that operator. That even if num j is equal to num I, j will not be equal to I. If j is equal to I, is the same process. If j is not equal to I, then these are two different processes. So, and one will go, one will not. So, you have something to say?
So what if like a process with, actually wait, hang on. So if like a process with the ID, I don't know, say like 2 arrives and then it goes into the for loop to like try all of them, and then like that's when it'll test like nums of 1. So like after that, what if the process with the ID 1 arrives and then it already like passed?
No, so if it already goes past, okay, so why he is asking, giving an example. So let's understand that example. So what he's saying is that, okay, let's say process 1 came, right? Process 1 came, and let's say all the nums are 0 for now, right? So process 1 came, so what will be the num for process 1? It will be 1, right? Or if everything is 0, max value is 0, you add 1 to it, so ID num for process 1 is 1. So now this process 1 goes through all the while loops, it sees that there is no other processes, so it goes into critical section. Process 2 comes in. What will be the num for process 2? Why?
The same number, so
No, process 1 is already in critical section. Now process 2 comes. So since process 1 is already in critical section, num 1 is 1. So what will be the num for process 2? 2, right? If process 2's num is 2, then it will try to execute this while loop, while condition. So it will see that num 1 is not 0 and num 1 is less than my num, because num 1 was 1 and num 2 is 2. So I will wait for num 1. You had something?
Okay, so this is just a point of clarification. So the line where you said the busy read, the reason why it's that is because you're accessing the I and the J at the same time, and you said it was like mutually exclusive, right? So that's the reason why it's busy wait and causing like is that the reason why?
Come again? So the busy wait is not to prevent processes from accessing I and J at the same time.
Okay.
It's just to block process.
Oh.
So busy wait. So whenever those two conditions get satisfied, you should not go. That is the idea. You can access I and J at the same time, at a different time, doesn't matter. So anybody has an example where this fails? Yeah.
So if num j is equal to 0, would it still execute the critical section?
If num j is equal to 0, it will not
Okay, so
execute critical.
This code just doesn't show that, but it'll skip over that.
No, yeah, so if you see this code, if a particular process wants to execute critical section, it will never have num equals 0.
So this only happens if num is not included.
No, it forces a process to have num non-zero. If it wants to execute critical section, you have to have non-zero num. Because you see, max num of all nums plus 1. You have to do plus 1. Max of nums cannot be negative 1.
But what if you're running it for process 3 and you haven't run it for process 1 and 2 yet? Then those ones would have num.
Yes, then process 3 will have num is equal to 1, and process 1, 2 will have 0. Yes.
They would run the critical section.
They will not, because let's say process 3 runs first, right? Let's say process 3 ran first. So num 3 is 1. Now let's say process 1 came in. So if process 1 comes in, what will be its num? 2, right? So it will break here, because process 1 will now look at, okay, j0 equals, will look at all the processes, right? So it will first look at process 0 has 0, so it will break it. Then it will look at process 1 is itself, so this condition will not be satisfied, so it will break the while loop. Then it will look at process 2 is 0, no. Then it will look at process 3 is non-zero, num of process 3 is 1. So then it will come and look at this condition. It will see that num3 comma 3 is less than num1 comma 1. Is it true? Because num1 is 2, num3 is 1. Num3 is less than num1. So this is true. Num3 comma 3 is less than num1 comma 1. So if that is the case, then it will block for the process 3.
What about the case where j is equal to I in the for loop?
Then that's the same process.
Then,
So you let yourself go. Right?
so the second half of the loop would be false and it would break down.
Yes, break. Doesn't matter because you have the same process. You should not wait for yourself. Right? Yeah.
If everything is equal to 0 and then two processes come in at the same time, so they both have this like token 1, does it go through the for loop at all?
Yes. It will go through the for loop. Why? Because even if two processes come at the same time, they get the same number. Their process IDs are different. If the process IDs are different, one will be greater ID, the other will be lesser ID. So whichever has the greater ID will wait for the lesser one. Any idea? Any other examples?
It's usually exclusive if you go to cycle processing.
It's not. It's not. Think about race condition. Think about the first line. What is the first line doing? It's calculating max, adding 1 to it, storing it. It's not a single instruction. The first line is not a single instruction. It's a lot of instructions. Right? So now let's consider two processes came in at the same time. All are 0. Let's assume that all the processes num is 0. Now let's consider two processes, process 2 and process 3. Right? Now I would ideally write it there, but I cannot write it there. Where should I write it?
You guys are on with the
Whatever?
There's white space.
There?
Yeah.
I need a lot of space. Let's write it here. So when you look at the algorithm, ignore the choosing terms and whatever is the rest of the algorithm we are using. Don't look at the choosing array, right? So let's consider that initially all nums are 0. So num is an array of zeros right now. Right? And then process 2 and process 5 arrive together. So they both execute the first line of code simultaneously. So first line here is the second line of the code because choosing is not there. Right? So if they execute the first line of the code, what will be num2? What will be the value of num2? 1. And what will be the value of num5? 1. Now let's assume that since these are large number of steps, calculating max, adding 1 to it, storing it into this num2 or num5, since there are so many steps, let's assume that the process 2, before it could store the value 1 into num2, it got switched to process 5. So what is the scenario? The scenario is process 2 computed the max. But could not store it. And got context switched to process 5. So do you understand this scenario? So process 2 calculated the maximum value, but it couldn't store it, couldn't add the 1 and store it. Before it could do that, you switch to process 5. And let's now assume that all the time quanta of the CPU goes to process 5. Let's assume. So now what is the value of num2? 0. Couldn't store it, right? So num2 has a value 0. What is the value of num5? 1, because it's getting the CPU quanta, it's storing it. So num5 is 1. So yes, num5 is 1. Then the next step is it will look at it will go into that for loop and will look for all the processes. It looks at process 0, num0 is 0. Right? It looks at process 1, num1 is 0. So it breaks for all those process 0, process 1. It looks at process 2, num2 is 0. So it skips process 2. Right? It looks at process 3, num3 is 0, skip it. Process 4, num4 is 0, skip it. Process 5 comes in, num5 is not 0. Right? Num5 is not 0, but this is process 5 itself. Process 5 is checking itself. So num5 is equal to num5 and I is equal to j. So that is false. So it again breaks. While loop. Checks process 6, breaks because num6 is 0. Checks process 7, 8, 9, 10, however many, process n. Checks process n, num_n is 0, so it breaks. So if it breaks for all the processes, it goes into critical section. So now process 5 is in critical section. Do you understand that there is nobody stopping process 5 from going into critical section? Right? Now let's say suddenly process 2 wakes up, meaning that you are getting some CPU cycles. Process 2 is now getting some CPU cycles. Right? So where will it start executing from? Since you store the state of process 2, where will it start executing from? Will it recalculate max? It won't, because it has already done calculating. So it will now store the value. So what value does it store? 1. So now num2 becomes 1. So that is after process 5 goes to CS, critical section. So now num2 becomes 1. So now num2, the process number 2 goes into the for loop, checks process 0, num0 is 0, break. Checks process 1, num1 is 0, break. Checks process 2, it is itself, so it breaks. Num2 is not 0, but then the second condition is num2 is equal to num2 and j is equal to I, so that is false. So it breaks the while loop. Checks the process number 3, breaks, num3 is 0. Checks process 4, breaks, num4 is 0. Checks process 5, num5 is not 0, num5 is 1. Right? So it goes to the second condition. Num2, comma 2, so now it evaluates. It evaluates, okay, this condition. Num2, comma 2, is it less than num5, comma 5? Is it? Num2 is what? 1. And what is num5? 1. So num2 is equal to num5. In that case, how will we distinguish between how will we find out the truth value? We have to compare the indices. Now we see that 2 is less than 5. So this condition will return what? True or false? What? Sorry, I made a mistake. J is 5. I is 2, J is 5. I is 2, j is 5. So it says num j comma j less than num I comma I. So num 2 comma, oh sorry again num 5 comma 5 less than num 2 comma 2 or not? So is it true or false? false. So this returns false. So it breaks on process 5. It checks process 6, num6 is 0. 7, num7 is 0. Checks process n, num n is 0. It breaks on all while loops. So then what happens? It goes into critical section. So P2 is also in critical section. So see, P5 in critical section, P2 in critical section, no mutual exclusion. Yes.
Okay, I'm getting really confused because you keep saying this, this is not mutually or exclusive, but when you look at the proof for the Baker theorem, it says that there's a theorem that it is mutually exclusive. Because, okay, I agree with like, the fact that before you said that has to start at 1, you cannot have it equal to 0, but they have like a proof where they show it where if you set I and J, it's like they prove it by contradiction. And if you have I and J set not to equal to each other, and if you put that through here, it essentially has it where num I is the same value as num J, which is why they prove it to be mutually exclusive. That's why I'm getting really confused why you're saying it's not mutually exclusive.
Don't read the book as we are going through the lectures. You read the book after we are done with the lecture. Right? So, is this the algorithm they used?
Yeah.
No, they used that one with choosing in it. And I said, don't look at choosing.
Okay.
Right? So that is the pretext. Now we'll look at choosing. So, if you didn't have choosing, this algorithm does not have mutual exclusion. Because we showed an example here. Right? This example shows that this algorithm does not have mutual exclusion. So why doesn't it have mutual exclusion? The sole reason is process 5 went on with the algorithm before even process 2 could store the value. Right? Process 2 computed the max, but it didn't store. Since it didn't store, process 5 didn't know whether num2 chose a number or not, or actually process 2 chose a number or not. Process 5 didn't know. So process 5 went on and went inside the critical section. Now after the fact, process 2 chooses a num, chooses a token. So to avoid that, what should you do? You should never go ahead without letting other processes that came in at the same time, without letting them choose a number, you should not go ahead. So whichever process come at the same time, you should let them choose their number first, and then you go, right? And that is the purpose of having choosing. That's why you have that array choosing. So what is that doing? That is saying that, okay, when you choose a number, before choosing a number, you set a flag. You say that I am choosing a number. And after you are done choosing a number, so after you are done executing that second line, then you reset the flag, 0, right? Now what you do? All other processes, you see the first while, before even checking the actual while condition, before even checking the loop, the busy loop, you first busy wait on choosing. That means if a process is not done yet, choosing a number, you wait for it. You wait for it to store the number. So let's say in our case, when process 2 computed the max but didn't store, what will be the value of choosing 2? It computed max but didn't store. It will be 1. So if process 5 stored the number and it came in here to execute that while loop while choosing j equals 1, if j was 2, choosing 2 is 1, process 5 will be blocked there. No? Process 5 will be blocked. Now if process 2 is done with the checking, right, or is done with the storing of the number, then it will do choosing I equals 0. Now let's say process 2 couldn't go into the for loop and you context switch to process 5. Process 5 was busy waiting in that while, so it broke from the while because process 2 is done choosing. It made choosing equals 0. So process 5 is done with that, it broke from that while loop, and then it goes to the second while loop. If it goes to the second while loop, it sees that num2 is not equal to 0. Now it checks num2 comma 2 less than num5 comma 5. What will be the answer? No, true. Because num2 is equal to num5 and j is less than I. J is 2 and I is 5. So 2 is less than 5. So process 5 will wait for the process 2. So this condition that we stopped, this condition will be stopped. Why? Because if process 2 did not store the value in num, process 5 will be blocked. It will not go and execute critical section. So this case is solved by using choosing. Now if you have choosing, then this has mutual exclusion. You'll always have mutual exclusion. So do you understand why you have mutual exclusion? You could only violate mutual exclusion if process 5 went ahead before process 2 could store the number. Right? That was the only possibility of contradiction. But using choosing, you forced process 5 to wait before process 2 could store the number. So you told process 5, okay, you have to wait for process 2, let it store the number and then you can go. So you eliminated that possibility of violation of mutual exclusion. So this Lampert's-Bakery algorithm has mutual exclusion. So now you read it. So today we will stop here. That is Lampert's-Bakery algorithm. Next we will go to semaphores, and that will be your assignment 2. Right? Assignment 2 has semaphore.
Assignment 2 has what?
Semaphore.